Hi, in this video I'm going to show you how I made a DIY battery pack using salvage lithium phosphate cells. I came across a 24 volt battery which made up of 8 strings of cells with 6 in parallel, which I've found that it wasn't lasting. There was obviously some faulty cells, so I've took that apart and I'm going to convert it into a 12 volt battery. Capacity will depend on how many good cells there are. Now, if you're going to build your own battery, it's much easier to just buy one. The short answer is
don't fuck about!
Because there's a lot of time consuming things you need to take into account. You need to make sure all the cells are balanced. They all need to be equal voltage, very similar capacity and very similar series resistance if you're going to be putting them in parallel, because if you don't do that, large currents will flow from one cell to another when you put them in parallel, potentially damaging the cell or causing a fire hazard. There's some essential things you'll need to buy, such as a universal charger like this, a battery capacity tester such as this one, and of course a standard DVM. Now, first of all, what I need to do is just show you these packs. These are 5.5 amp hour lithium phosphate cells. I really wouldn't recommend building your own battery pack out of lithium ion because it's just too dangerous, whereas lithium phosphate is a much safer type of battery to use for DIY battery packs. It's less likely to explode, especially if you're going to be putting them in parallel. So what we need to do now is rewind to a few weeks ago. When I started this project. Hi, welcome to another video. Today I have got a lithium phosphate battery pack which is defective. It doesn't last and it cuts out intermittently. Now this is a 6P 8S configuration, so nominal voltage is 25.6 volts. What I want to do is convert this into a 12 volt battery. The cells are approximately 5.5 amp hour each. So it gives it a nominal capacity of about 32 amp hour, give or take half an amp per hour or so. I want to convert it into a 60 amp hour 12 volt battery. Now, it comes with a smart BMS with Bluetooth on it. So I've charged the battery pack up and I found that the cells are quite out of balance. And if you look at this sheet here, I've done a few voltage, we made a few scratchy notes. They are at rest voltages, and then the voltages that would have just come off full charge. And as you can see, one cell in particular hits full charge before all the rest. Cell number 7 hits 3.65 volts. And all the others, particularly cell 1 and 3, they're still at 3.37. So it's out of balance. So I think what we need to do is charge all these cells individually to full charge. Each bank of 6 cells, charge them all to full charge. Then when they're fully charged, do a discharge test on them and then write down the capacity. That will give me the best pair of cells to pair with each other to put in parallel. So there'll be 12 cells in parallel instead of 6 to make it 12 volts. So that's the first step with it. And then the second step is to number all these cells here, like 1, 2, 3, etc. So what I'm going to do is dismantle this battery pack so that it's each individual cells. Because if one of these banks of cells gives a much lower capacity than all the rest, it would indicate that one of these cells is faulty. And then when I dismantle it all, I'll be able to tell which is the faulty cell. I could test each cell individually, but that would take an obscene amount of time. So it's probably best to test each bank of 6 cells at once. Then obviously the lowest one would be the faulty one. Then you can dismantle that pack and then determine which is the faulty cell within that string of batteries that are in parallel. So first of all, we need to do, this has been sat for a week. So I've opened all the edges of the cells. So what we're going to do is put that one on charge by using this universal charger. We'll set this to lithium phosphate charge, rated 2 amps at 3.3 volts 1S. So what we're going to do now is connect that to this battery pack. Connect it across the first cell, so the negative wants to go on the negative lead here, not via the BMS of course. And then put the first one on the first cell. And then what we'll do is that, set that to charge. And that's charging. So what we're going to do is repeat that for each of the 8 cells that are in series, each bank of cells, until they all reach full charge. Then we'll do a discharge test on each of these cells, these banks of cells, and then see which is the best one. And then that will determine which are the best ones to pair with each other. Because obviously you don't want to pair a battery that's weaker than the other, because it will cause high currents to flow. If one cell is seriously discharging, the other one is charged, so they must all be the same voltage, same capacity, give or take. Small amount of capacity, perhaps 250 milliamp hour or so, and they need to be the same in series resistance as well. So we'll do that, and then we'll come back, and then next step will be to label all these up, dismantle the battery pack, and then we might determine if one of these individual cells is faulty, if one set of 6 cells gives a much lower capacity than the others. So this charging is probably going to take the rest of the today, so we'll come back another day. Right, so it's much later in the day, and as you can see, I've charged these batteries up to full charge, and this is what capacity has actually been put in them. You can see there, 4.5 amp hour on one, 408 milliamp hour on the other one. Cells 4 and 7 are already pretty much fully charged already, so this just shows how badly out of balance this battery pack is. Now, that could be because it was never balanced properly in the first place when this battery pack was assembled. I've almost certainly got some faulty cells, I would guess. Certainly be a faulty cell on there, a faulty cell on there, because they're charging first before all the others there, so that would indicate there's a weak cell there somewhere, because they've got less capacity than the other cells. So it's definitely, the next step now is to remove this BMS, dismantle the battery pack into the individual banks of parallel cells, and do a discharge test of each set of 6 cells in parallel. So like I say, we've got 8 sets of cells with 6 in parallel, so approximate capacity of 30 amp hour. So I'm going to put them in a discharge test and write it in these boxes here, and then that'll give me an idea of which cells are faulty and which pairs of 6 cells I can put together. It may turn out to be a 30 amp hour battery pack this after all, so I think if I use some faulty cells, I'm going to have to put a battery pack together out of all the good cells and then see what I've got left over. It's a very time consuming process, so this is going to have to be done over a period of a few weeks. It just goes to show you can't simply tell a battery's capacity by the voltage alone. You must do a discharge test, recharge it, and then test it again. That's the only way you can tell what the true capacity is. Now if I'd have just put all these in parallel, like say cell 7, cell 8 for example, since I put 5 amp hour in that one, if I paralleled 7 and 8 together, you get a bit of a problem, because when it reaches low cut-off voltage of one cell, the other one we're putting a lot of current into it, and that'll lead to the cell overheating and possibly fire, so it's definitely a no-no. So yeah, I'll put this aside for a few days and I will test all these cells and then come back in a couple of weeks or so. Well, the results are in, and done that test on these cells. Tested each string, each bank of 6 cells, and discharged to 2.8 volts per cell. And as you can see here, there's at least 18 cells here, which I know are good. These cells have got a capacity of 5.5 amp hour, so that works out at about 5.1 amp hour each. So I've got the bank 2, bank 4 and bank 7. Very similar capacities, so I don't need to test them. So I know them cells are going to be good. What I'm going to do is that one there, cell number 8, looks like a good one as well. So that's fairly, oh no, cell number 5's higher capacity. So they're probably going to be good. But we definitely got a faulty cell on bank 3 because during charging, one of the cells gets hot. So that's a sure sign of a failure. So definitely to test them cells individually. But like I say, there's at least 18 cells here I don't need to test. The others I'll test individually. I'll do that by fully charging them up and discharging them to 2.8 volts like I did with these. And then I'll see how many good cells I've got, and then we can build a battery pack. Right, it's later in the day and I've got a pack of 6 cells here. Some are obviously faulty because they get hot whilst charging, and they've got a capacity of around 4.96 amp hour when discharged at 2.8 volts per cell. Some have all got 3.6 and 2.9. So if we look at the internal resistance tester on a known good battery, let's see, it's about 7 ohms, 7 milliohms, yeah, 7.04. So that's a known good one. 7.05, and then this is a bad one. You see, yeah, 17 milliohms. So we don't even need to test that any further. We know that's a bad cell. 17 milliohms. So it needs to be about 7 milliohms to be good. That's 6 milliohms. 6.96, yeah, that's a good one as well. Yeah, that's a good one. But the capacity on that one's only 4.51 amp hour. It's slightly out of spec. All the others are about 4.9 or just over 5 amp hour. And I say that's the 2.8 volts per cell. This one's all given 4.51 amp hour, so that one's slightly out of spec, so I can't use that. So you're going to test the capacity and the internal resistance to make a good match. So that's 7. That one, that's a good one. And then finally we've got another bad one here, which again, measure that one. Meter's a bit consistent. Yeah, 12 milliohms. Yeah, so yeah, definitely need one of these series resistance testers for matching cells. Just go back to that one that was giving a lower reading. There, 3.32 is 7. Compare it with this one, 3.331, 3.3329. So yeah, so that's something what you need to do. So I think I've got one bank of cells to test now, and then I can start matching them up. At the moment, I can make at least a 45 amp hour battery pack using the 9p 4S configuration, but if I can get 8 cells, I can make 11p 4S configuration and have 3 cells left over. 4 cells left over. So, which will probably be these here, the 4.51 amp hour and the 3 faulty ones. So assuming all the ones on this next pack here are good, which I'm currently testing, I can make a 55 amp hour battery pack. So yeah, very important. Now this tester would only £35. Apparently it's got Bluetooth on it and all sorts, but that's for another video, is that. When I've tested these, the next section of the video will be actually putting the battery pack or battery packs together. Right, so it's been a week or so, and I finally got the battery pack assembled. It's been able to sit for 24 hours to all the cells equalise amongst themselves with them put in parallel. Now we just need to check some voltages. But then we can connect the BMS up. So that's your negative, your positive. So let's put it on one side. Quite heavy. So negative, first cell 3.11. As you can see it. 3.11. Cell 2. 3.12. 3.10. And 3.11, so they're all within 10 millivolts of each other, so they're all relatively balanced. And obviously what I'll do there, I've done the bottom balancing by discharging them all to a certain level, then allowing them to rebound and discharging them again if necessary until they're all the same voltage. And what we're going to do now is once I connect to the BMS up, allow it to charge, and then if necessary might need to do some top balancing as well. But for now, just need to get the BMS connected. Now the BMS I'm using is 30 amp 4-cell BMS. It comes with a cables, a Bluetooth module as well, so I can monitor the cells remotely. Now I just need to figure out where I'm going to put it. So that's your positive and negative. So one of these is that's C minus, B minus, so that one has got the negative of the battery, which is there. So ideally it needs to go in the middle. Right. Let's get a piece of this insulating board and we'll place that over the side of the cell. Like so. Right, then it's get the BMS, so we'll put that. Some rubber feet. Just want to keep that wire, keep the negative away from anything that might touch. And this needs soldered into the battery pack. So let's get the BMS connected up and then we can go from there. Yeah, the biggest problem with connecting such a large amount to there, it's going to be quite difficult to solder that. So I need plenty of solder. Let's get that on there. Right. Right, what I might be tempted to do is just remove this so the heat isn't going to the cells. Just keeps some of the heat away from the cells and not directly transferring into the cell. There's little copper washers under there to help with the heat. So electrical connection. Right. What to do here is solder that on there like that. First of all, put some more solder on the cable. There's shit some more on here. Nicely soldered. I can tighten the cell weights back up again now. What I'm going to do now is take the opportunity to just make sure all these connections are tight. Then I can check the resistance between the contacts with this internal resistance meter. I say the internal resistance meter is just basically a milliohm meter, so we can use that not only for testing the internal resistance of batteries, we can also use it for testing the resistance between the contact and the strip. So 0.66 milliohms on that one. I can't get that one on there, but 0.66 again. Then we'll repeat that for every single connection. Just 0.62, 0.55, 0.58, 0.65. I'll repeat that for every single cell. That will reveal if there's any bad connections between the cells, which will cause high resistance and cause it to get hot. So I'll just do that now and then I'll come back. It might seem like I'm skipping a lot of it, but I'm sure you don't want me to see. You check every single connection. I don't want the video to go on too long. Notice one here straight away that's a bit could be nice and tight. I'm sure they're all nice and tight. Right, so now what's the bounce wires? BMS comes with what that bit's for. So there's no instructions with the BMS. And don't know what that one's for, but plugs into that port there. Let's have a look. AB. I think that's the RS485 connection, I think. Either way, I'm not going to use it, so right. Get to the Bluetooth module. Put that into the UART port. And zoom that camera out a bit more so you can see that. And this needs to be placed somewhere. Ideally. Oh, it's a sticky label for the Bluetooth. So you can scan it so you can use the app on your phone. That's what that is. Right, so I need to put that to one side. I don't need to make sure I don't lose that. And this wants to go wires can be nicely lightly tied up. Like so. Right, so I'll put the balance wires on now and fit the temperature sensor. The temperature sensor ideally needs to go right into the core of the battery pack. the wires where they won't chaff and anything. Yeah, there's only one temperature sensor on this, so it's a bit awkward. I can't put it down there, so it's going to have to go to the side. Get it far in there as possible. It's easier said than done. I'm just going to tuck that down the side of one of the batteries. I posted a bit of Captain tape over it. Right, balance wires now. Now the first one is B0, so that must go on to the negative. So pass that through these wiring looms here. I don't want to plug into the BMS, so I've connected it to the battery and verified all the voltages are right. So that down there. Yeah. So, all well and good now. Plug the BMS in. Why didn't that fit? Ah, there we go. Blue lights come on. See the blue light come on there? That indicates the BMS is working. And there we go. All I need to do is tidy it up now. And then we can give it a test. What I'm going to use for the positive is 2 automotive fuse holders. There's going to be 2. One's going wired to a cigarette lighter socket, the other's going to go to an Anderson connector and one of a USB to USB-C panel mic type thingy jobby. When I put that in the case, which I'll show you later in the video, Just need to get the positive terminals soldered on now. Right, so that's the two positives that we've got, two separate circuits. I think all we need to do now is really charge it up, and then if necessary top balance it, put it all together, and then give it a full discharge test. And it's getting quite late now, so I think that's going to be a job for another day. And here's the wrapped up battery pack, wrapped up in fireproof epoxy resin board. Two positives, your main negative. This little board on the side here is an active balancer, which I use to top balance the cells. That I'm not going to leave plugged in permanently because the BMS does a pretty good job, but if the cells start to get out of balance, I can always plug that in. And what that board will do is shunt current from one cell to another. It's got a 1 amp balancing current, so it keeps the cells in balance without having to strip the pack apart and manually rebalance it. I shouldn't have to do that with a good quality BMS and decent cells. That's the barcode, QR code thing for the Bluetooth MAC address, so I can pair it with the application on my phone. Yeah, parcel tape's good enough, but that'll be okay. That just needs to put it in the case now. Hello, right, now it's time to case this battery up. I've got a Seahorse SE520 case I got off eBay for 50 quid, in very good condition, so I'm going to use that. I'll try and get this all in shot because it's difficult with the lens of the camera. Let's see what I can do about that. Right, I think that'll work. Right, get the cell. Right, that'll fit in there like that. Then cigarette light socket will go on there, and also the charge connector. I'm going to have a USB interface thing as well. So, right, that's going to go in there just nicely. To one side, take that out for now. Then we'll start drilling. Right. Standard cigarette lighter socket, which will go there. Charge socket there, and USB interface in the middle. Right. The USB interface charger type thing, which will go there. Charge connector right at the end there. So let's go out there. Perfect. Right, now with this case being quite thick and that being a cone jaw, I have to drill that now from the inside. It's like counter socket. Right, that's all the holes drilled. It's preparation for the case. Right, got all this mess tidied up and then fit it all together. Oh, right, what a mess that made. Right. Get the little thingy. So this will have a 24 watt output and Anderson output. That's a 12 watt cigarette lighter socket output, an Anderson output, and a USB-C power delivery charger. So the Anderson connector was a very tight fit. I didn't want to force it. Right. What do I do with the positive? Right, well, I think I have to splice it into there somehow. And I'll wrap it through there for now. Right. See how it works. So control panel there. And it works. There we go. Right, just need to find somewhere securing the battery and then job's a good one. So the aim is to protect the battery pack as much as possible. Also down here I've got a little active balancer board, so I don't want to crush that. This case is go it that like that. And just some foam in there now just to stop it from sliding across. There's some packing foam in there just to stop it from moving about. There, that's not going anywhere in that. Right, so let's make a piece on the top. And I don't want too much in there, it's a bit of a high risk. So. Right, shut the lid. Hopefully it doesn't rattle. There we go. Right, so stay inside. There we go. Spare fuses. And let's put them inside there. Right, seal it up. And job's a good one. And that's for charging it. That's your USB and your cigarette lighter out. And that's the complete battery pack. If you made it this far, thanks for watching.